Hey, all right. Hey, welcome here, students, again to the next lecture on our modern physics. I guess this would be our third one. Same predicament that now that I'm on camera, as I needed to start it. I don't have a camera person. We'll just kind of do the same thing as the last lecture, and let's just kind of focus in right here on this one whiteboard. And so I'll transition between the computer and the screen and go back and forth. And so hopefully everything will make sense out of this. Okay, now we are ready to continue on to the next level, if you will. And I just noticed my ink here is kind of low. Bummer. Should have caught this ahead of time. And I don't have my ink real close. All right, never mind. Why don't I just use a different color besides black here? All right, so let me use a blue here. So working here with the blue, not that it matters, is let me point out what we're going to be doing here. We're going to be looking at chapter 30. It's called Atomic Physics because we are going to look at the consequence, I should say, of the physics that we learned earlier. We called that quantum mechanics. And we started off with Planck saying, hey, what would happen if, and so he's kind of the beginning one, what I call the birth of quantum mechanics, and said, look, the birth of quantum mechanics, it was the first time that somebody took this idea of saying the world could be quantized. And as I said before in the last lecture, Planck didn't believe it, but nonetheless it explained the result. And then Einstein did. Einstein was ready to go one more step and not only be brilliant but also be bold and say, well, that's the way it is. Then we did Compton, but finally we got to de Broglie, and I left last lecture kind of giving you a reason why things have to be quantized. And I want to pick up on that later on here as we get started. But I want to point out then that like the last chapter, and as we come to an end, your author tries to do a lot. We just don't have enough time. And so let's look at sections 1 through 6. And as you'll see here, kind of the meat of it is section 3. You'll see that section 5 says here's a bunch of practical applications. So I'm going to let you kind of read that. I won't necessarily lecture too much on it. I think by the time you see sections 3 and 4, kind of the meat of it, 5 will kind of fall into place. So I'm going to encourage you to just kind of read 5. But that being said here's where your author starts. And in sections 1 through 2, he begins to start off and tries to get you to understand atoms in general. What do atoms look like? So starting with our current understanding of the physical world, and I'll go back to classical first. And so before the last lecture, before we got into quantum mechanics, let's just point out what our atom would have looked like. Because this, I think, you've been exposed to in a combination of maybe some college classes, but most likely a high school class, or maybe even a middle school class. We call this kind of the planetary model. I'll give you a little picture here. It's nothing probably much different or beyond what you've seen or what we've already talked about earlier on in this semester. And that is, in the center is this little bundle called a nucleus. And then an expanded view right here is to say the nucleus itself is made out of protons and neutrons. And it's not shown in this picture, but as we mentioned earlier on, we could even go further down. I see for a while science thought that was maybe the end of the road. In fact, that's why they called them atoms. They even thought that was the end of the road. But they learned that atoms were actually made out of smaller things, and they learned out that in the nucleus there were two things called protons, which they color in brown, and neutrons, which they color in green. And so they say that they're down here in this nucleus. And then the stuff orbiting around like little planets, that's why we call this a planetary model, kind of in their mind is like, hey, isn't this behaving like a little solar system? And so, yeah, it is. And so these blue things are electrons going around. And so that's kind of the model you already had, and take that with us. That's where we'll get started. That's our understanding of the atom before we thought of the electrons as waves. And so I want to take this model one step further. But I just want to kind of review this model and get some terminology out here, just in case you were not all that familiar. And of course, that's what your author does in the first section. So section 1 and section 2 of this is kind of a description of how we understand it. Now, I might want to get in a little more detail. I'll put some numbers on the board once I put up the screen, but what is the size of this nucleus? What is the size of the atoms? Oh, I think I was beginning to say that these we've found in recent decades that the proton is made out of quartz, and actually for that matter, so is the neutron. And so it doesn't really change too much. Instead of having two things called protons and neutrons, now we got two kinds of quarks, an up quark and a down quark. And if you group them together, let's say I guess two ups and a down kind of group together, and that's called a proton. But two downs and an up, when they group, that's called a neutron. And so we've learned that it's a bit more complicated than this picture shows. But like I said, that's not usually kind of a high school model, and this is trying to kind of show you a high school model, so before we understand the particles called quartz. But over here looks kind of messy, and I'll just point out that they've got some blue orbitals. There's just two of them, and so two electrons, and so again the electron's in blue, but if you follow the blue line, they kind of orbit kind of on an inner path as opposed to an outer path. And so the other electrons in blue, which kind of have this brown orbit to them, and it looks like there's 6 of them if I count right. 1, 2, 3, 4, 5, 6, yeah. And so a total here of 8 electrons, 2 of them in what we would call an inner shell, and then another, I guess it would be 6 more, but as we'll see in a moment, we could get as many as 8 in that next shell. And then there would be a 3rd shell and a 4th shell and a 5th shell. And just to give you some added information, maybe beyond what you might have done in a high school, is we start labeling these shells. And in the old school thinking, we called them, the inner one a K, and then just followed the alphabet. K, L, M, N, O, P. So you can see that your author put here K shell, 2 electrons, and kind of points to this blue one. The L shell, let's see, did I say that right? A, B, C, D, E, F, G, H, I, J, K, L. Yeah, so K, L. So the next one, the L shell, would have, and he doesn't show it anywhere here. Oh, here he goes, L shell right there. Oh, he does say there's 8 electrons. 1, 2, 3, 4, 5, 6. I only see 6 in the L shell. And then 2 for a total of 8. 1, 2, 3, 4, 5, 6, 7, 8. Yeah. So I don't know what he means here. Maybe he means total is 8. Because that's what it looks like to me, total 8. And it makes sense. I'll look at the periodic table. I think 8 is oxygen. Yeah, so this would represent an oxygen atom. And let's show a periodic table here in just a second. But like I said, this first step is just what does the atom look like when you think of them as particles? And so we've got the protons and neutrons, which we're going to think as particles for a moment. In fact, we'll never probably change that. We'll just always think of them as particles. We'll just only think of our electrons as wave. But I might as well add that the next step in the development of quantum mechanics is, who is it? George Gamow says, well, wait a minute. If de Broglie had success thinking about the electrons as being a wave, what about the nucleus? What about the protons and electrons? Could we think them as waves? And could we understand the behavior of the nucleus better? And the answer is yes to that. And kind of a little nice in part of that is he was connected to UCSB here right locally, as well as I believe University of Colorado. But anyways, another brilliant mind in the development of the physics. So this, like I said, is going to be our model here, and I'll just add to this picture a periodic table. And this periodic table has more information in it than most people actually realize. The way it's laid out is absolutely fascinating. But I will point out, first of all, that if you read across in the rows, the numbers, what we call the atomic number, just adds up, and it goes 3, 4, 5, 6, 7, and you can read across the rows. So it goes 1 and 2 across the top, then 3, 4, 5, 6, 7, 8, 9, 10. Then another one is 11 and 12, 13, 14, 15, you know, and then I guess that's row 3, then row 4. And so we've got the rows listed here. But they're also color-coded. That's kind of nice, so they're in blocks. And each of these has some very important meaning, and we won't obviously talk about all the pieces of the meaning of the periodic table. But what I do want to say is each row represents where the electrons are as they get piled in there, starting with row 1 being the K shell. And remember, I was just showing you a picture that had 2 electrons in the K shell. And so right here, 1 and 2, you can see that that fills up the entire K shell, and then we start something new. Now, when scientists first started making the periodic table, the reason they called it a periodic table is it looked like there would be the atoms, you went across, and then as you got to more electrons, they repeated themselves. So they put everything that seemed to have the same chemical behavior in the same column. So let me pick on oxygen for a moment. And so they noticed that oxygen seemed to behave a lot like, that must be sulfur and selenium. And they just put everything in there. And the reason is, now we can understand, is that when atoms interact, it's the outer shell that interact. And so if they have this filling process, you would put some in, and once they're filled, you start going to the outer shell. Let's say the outer shell only has 1 electron, which, by the way, in this periodic table would represent this first row. And so hydrogen has just 1 electron in its K shell. But then when you put a second one, you fill that one up, and if you then put a third one, you get lithium. And so notice it's 3. 3 means we've got 3 electrons, at least in its normal state. We can make it an ion by adding electrons or taking them away. But in its normal state, it has 3, which means it has 2 in the K shell and 1 in the L shell. And that second shell, and maybe I should start using first and second, because that's more of the modern language, first shell, second shell. We call this the principal quantum number. And so right here, these are the principal quantum numbers. K and L is kind of old terminology, but I think it's good you get exposed to both here. But what I am trying to say, whether you want to call it first and second shell or K and L shell, is that lithium would behave a lot like hydrogen because the things that interact are that outer shell. Those are the things that touch other atoms. And so if you only have 1 in the K shell, or the first shell, and 1 in the L shell, or the second shell for lithium, as they interact, they're going to behave the same. And that's the lesson I want you to see. That's what this section 1 through 2 is what is the periodic table? Why is it laid out of this? What is a K shell? What is an L shell? What is a proton? What is a neutron? What is an electron? How big is the atom? How big is the nucleus? How is it all spaced out? All of this without introducing the whole idea of quantum mechanics and waves. Because then the rest of the chapter is going to throw that in. And so we're going to mix what we already know from chemistry classically and mix that in with the last chapter, which is the wave nature, and get a better understanding of what we call the physics of the atom. And so the title of this is Atomic Physics. What is the physics going on in the atom? Why does it, say, give off the color of light that it gives off? Why does it chemically react the way it does? Now, we won't go too much that, because that's kind of overlapping in chemistry, and you kind of touch that on chemistry. But what you don't do in chemistry so much is explain why this happens. You just do a lot of things of, oh, this does happen. Like, you know, oxygen has 2 bonds, instead of saying why it has 2 bonds. And, you know, for you guys in life science, it's the middle ones that is amazing, especially carbon, because carbon is 4, it's right in the middle. It can take electrons, it can take it away, and there's no other elements that have such just an incredible amount of bonding. Silicon's close to that, and that's why we use silicon as, from an engineer's point of view, from my point of view, silicon's the amazing one, and we can make, you know, semiconductors, and we can make microprocessors because it behaves a lot like carbon. But when it comes to life forms and the chemical reactions, the biochemistry, you gotta just love the craziness and the complexity that carbon can do. And so there's carbon and silicon right on top of each other, and all those have basically the same chemical properties. They begin to change. They're not exactly the same, but there's something about them that behaves. So, like I said, with that in mind, I'm just trying to kind of give you an idea of what probably most of you already know, but some of these may not be so new to you, like the number of shells and labeling them K and L, or even just labeling them 1 and 2. The fact that they're a proton and a neutron, I think for most of you've got that here. Anyways, looking at this periodic table, I want you to see the numbers, and they're just called the atomic numbers, and they just order up, getting bigger and bigger and bigger. And what they actually mean, technically, is the number of protons. But the number of protons, because they're positive, like to match with the number of electrons. And so for the neutral atom, they would be equal. So remember, go back to the beginning of this semester, positives and negatives attract each other. And so if you don't have the right number of electrons to match the number of protons, nature will try to get it that way. Now, it doesn't mean it stays that way, because those electrons might be having a battle, and if they don't match, that's what in a chemistry class we called an ion. And we too will call that an ion. But we're going to really look at the neutral atom. And so because when we look at the atomic number, we're going to say that's the number of electrons. When technically it's the number of protons, okay? Then the number of neutrons, we don't need to really get into that. It's not even shown up here, but there's often a second number called its atomic mass, or its nucleon number, and that tells you how much the total is. Now, this periodic table, which you can't see from where you are, but if I look over at oxygen, oxygen has an 8 for the atomic number and a 16 for its atomic mass, or sometimes called its nucleon number, because that's how many are in the nucleus. So if 8 of them are protons, then the other 8 must be neutrons. And so I know by looking at this periodic table how many neutrons I have and how many protons I have. But let me not say too much about neutrons, because that's not really going to come into play in terms of the physics. It's the positive, the negative that interact. And we'll talk more about that in future chapters anyways. So we'll worry about the nucleon number or the mass number, like I said, a little later here. But right here, I just wanted to point out the numbers. And that's why the picture I was showing earlier, I called it oxygen, because I counted 8 electrons. And so if it was neutral, it would have 8. And that's what the 8 over the oxygen is meaning. That's what it's saying, 8 oxygen. And that's how I knew it was in 2 shells. I knew it was in the second row. And so the first row, the K shell, or the first shell, whatever you want to call it, had 2 electrons in it. That was labeled in the blue. And then we started adding electrons and got 6 more for a total of 8. And that's why I said you could actually fit 2 more and get a total of 10 and be like neon before you would start adding electrons on another shell. And so if we got to a total of 11 electrons, we would be right here in sodium, and we would be in that third shell with just that one on the outside, and that would be the one that would kind of determine its chemical behavior. So because of that, sodium would act a lot like lithium, which acts a lot like hydrogen. All of them have just 1 electron on that last outer shell, the one that does the most interacting. Okay. So I think I kind of touched on enough to get us started, but I do want to say then, as we go along here, we're gonna have to call up the periodic table periodically and say, hey, what is this? How many electrons does it have? What shell are they in? Okay, and so keep that in mind. But I also wanted you to see that atomic number. That atomic number tells us how many electrons are there, and the row tells us what shell they're in and how many are in each shell. Okay, so like I said, that's probably the best place to get started here. Now, let me go to another picture and jump into a little more of the nuts and bolts here of your new material. Assuming you already knew that, or now you know a little bit how to picture an atom. Oh, you know what? I said I would give you size. Okay, hang on. This could come into play, not so much this chapter, but later on. But I should say that if here's the nucleus, and I'll just draw it as a round blob. Remember, there's a bunch of protons and neutrons, and so again, as we said for oxygen, you might think of this as 8 protons and 8 electrons buried in here. And then there would be the electrons going around. And again, if it's oxygen, you might say there's 8 of them. And there would actually be 2 shells. So maybe I better put something like this. In fact, usually in a chemistry class, we do something like this. And we say, okay, I'll put 2 in the first shell, the first orbital. Whether we call it 1 or K, doesn't really matter. And then I'll go to the second shell, the L shell. And I got 6 more. And so I'll put them in, and they usually like to spread out, and then they like to double up. And so I'll do that. And so that would be a good representation, kind of in a planetary model of what you might see in a high school or a chemistry course or a physics course where you didn't really get into the wave nature. And so again, this would be what I would call a classical model, classical physics. What does the atom look like before we got into these chapters on modern physics? And now we want to look at kind of the behavior when we think of them as waves. That is the electrons, not the nucleus. But as I was saying here, it's probably worth putting here some dimensions on here to give you a better feel for the atom, because the diameter of it is about 100,000 times bigger than the diameter of the nucleus. So the nucleus is 10 to the minus 15 meters, and if you multiply that by 100,000, you get 10 to the minus 10. And so when we start asking, okay, what's going on in this atom, most of this is empty space. In fact, if you want to do kind of a scale factor here, I like to say take the nucleus and let's blow it up to about the size of our football field or soccer field down here in our stadium. So, 100 yards or 100 meters long, and say, okay, that's the size of the nucleus. Multiply that by 100,000, and that's where the electrons are. And so for here in Santa Barbara, that means the electrons are way over on the East Coast at New York. And just a lot of empty space in between. And so that helps with your visual model of why you call it a nucleus, because all the mass is really right there and the rest of it is almost empty space. And even the electrons are something like 1,836 times lighter than one proton. So again, all this mass is really concentrated in a small spot. And there is some stuff on the outer rims, but most of the atom is empty inside. And that comes into play. I don't think we'll kind of get there, but looking at some astronomy stuff, what's called a neutron star is absolutely amazing, because gravity is so strong that the nucleus of all these things come together. And if you were to pack all the nuclei together so there was not any empty space, kind of a teaspoon worth. When you pick up a teaspoon of water, you go, okay, I can feel that weight. It's not very heavy. But remember, most of it is empty space. If you were to pack all that in, 1 teaspoon would be hundreds of thousands of tons. And it's just weird to think about nature in that kind of position. And again, it just doesn't feel right with us, because that's not the world we live in. Our atoms have space to them. And to pack them in so tight and lose that is just kind of bizarre feeling. Okay, well, let me keep going, because like I said, I wanted to begin by just making sure everybody's got a good feel, and that's what your author says, a good feel for what an atom looks like. Okay, so then let's throw in the wave nature. Let's throw in this last chapter on Bernoulli's idea that we're going to change our thinking from saying that the electron is a little particle going around, so the Earth orbiting around, to a wave. Okay? Now, hang on just a second. There's a little problem at the back door here. Let me just see if I can fix it here. Okay, I think that's good. All right. And just close it. I don't know if you could pick up all that sound, but there's looks like a lot of activity, a bunch of skateboarders going down the staircase over there. All right. So I just want to close it and lock it, make sure nobody comes in here. Okay, now, that being said, your author does a great job of trying to show you here what I was trying to show you at the end of last lecture. And that is the reason why we have quantum mechanics. And so your author starts off with saying, let's just take a string between two tied ends like I did on the last lecture. And I won't bother to hook it up again, but I at least decided I should bring it out here today. And so I just, when I took it apart, said, okay, remember this, right? Remember, we could have one end tied and the other end tied, and then we can shake it, and it can shake in a mode like this, or we could shake it a little faster, and it can be in a mode, whoops, something. And I'm not sure if I can do it just holding it. Here we go. Or it can be in something like this. You know, but the point was that now the wavelength and the frequencies are quantized, and so thinking of things as a wave hopefully is not a surprise of why there is quantum mechanics. I would say there is quantum mechanics really for the same reason there is the quantizations of the frequency on a guitar string or a piano or a trombone. It's just not as surprising. And so that's really kind of a big emphasis I want to keep getting across, because I really want you to understand not only do we need quantum mechanics, because that's what the experiments say, and what is quantum mechanics, but why we have quantum mechanics. So that's what the physics does, is why we have the quantum mechanics. And so your author's trying to say the same thing. But he does point out that for an atom, this would kind of be around the circle. So in other words, let's stop looking at this and hook it around in a circle. And so he looks at what he calls figure B and figure C, and he says, think about the waves, and again on a string they go down and bounce off and come back and down and come back, and see what they do is they begin to interfere with each other. And our argument was, back when we did our acoustics, that if they came back and they didn't line up just right, they would have destructive interference and then the wave would go away. And in this case, if they go around a circle, and so this one is trying to show something like this, so we go around, there's one wavelength, another wavelength, and another wavelength. So I would say around the circle has 3 wavelengths. And then when you get back where you started, you would have constructive interference. But if you did not get back to where you started, and that's what picture C is trying to show. Picture trying to see is say, okay, if you went around and you were off a little bit, then as the waves go around, you get destructive interference, and kind of thinking of the whole thing as one big pattern of constructive and destructive interference. If they're just off by a little bit, they interfere. And if they interfere even a little bit, the second loop around would only have partial destructive, but the third would have even more, and the fourth. And so a stable atom, which would have this wave going around millions and billions of times every second, would get you with destructive interference. And then you'd get nothing. And when I say nothing, I mean the wave is gone. And remember, the electron is the wave. And so this is our explanation of quantum mechanics. This is our reason why you have to have it just right. You have to have it quantized. There's only an integer number of wavelengths around the circle. And so Bohr is going to run with this. Bohr is going to say, and maybe I should call this a modified Bohr model, because he starts off by just saying the angular momentum around the circle has to be quantized, and doesn't really give a reason why. But he gets some amazing results. It's later on, as we begin to think of them as a wave, and so now today we call this the modified Bohr atom. And it's not the full picture because it's not three-dimensional. I mean, you can see that now, that this wave is just kind of going around a circle. What about waves that would be coming in and out? And he doesn't take that into effect. So it is kind of amazing that he gets such amazing results, because it's less than perfect. And then the next player in this quantum mechanics is Schrödinger, who says, well, let's look at waves from a three-dimensional model, not just a simple around the circle two-dimensional plane. And like I said, I think it's actually kind of amazing Bohr got as lucky, I shouldn't say lucky, it works, results, when it's not really a complete model. But it's such a good model, that's what I want to share with you, and that's what your author shares with you. And we won't necessarily go as far as three-dimensional. You start trying to draw waves in 3 dimensions, it's really hard. And that's what I was saying on the last lecture. That's what you tried to do in your chemistry class. You talk about these s orbitals, these p orbitals, these d orbitals, these f orbitals. These are all drawings of somebody trying to represent what a 3-dimensional wave would look like. And on a picture, they don't oscillate, so it's hard to tell it's a wave. But even then, because you're trying to draw 3 dimensions on a piece of paper, and I really even say you need a 4th parameter, because you're trying to draw 3 dimensions in space, and where you draw them, you're trying to draw an amplitude. So how do you draw an amplitude plus the 3 dimensions of space? So you got 4 parameters you're trying to draw. Plus it changes with time, so you got 5. And how do you draw that on a 2-dimensional piece of paper? And it's not easy. And so that's why I think interpreting these orbitals from a chemistry class is something that a lot of people who take beginning chemistry kind of struggle with and just kind of have a rough understanding their first time through chemistry. And maybe if they go on to physical chemistry, then the pictures begin to say, oh yeah, I see. You're trying to represent a wave that, of course, changes with time. It's spread out in 3 dimensions, x, y, z, and it has an amplitude. So you're trying to draw 5 parameters of this wave in a 2-dimensional setting. Not easy to do. So, I digress, but I am going to say then that we are going to have a pretty good model, but not as far as we know, not the best model that we know, but it is one that will help you to get ready for the next step. And so baby steps here. And so we're just going to take you from your high school model up to what we call the modified Bohr atom. And so let me say it again, because I wanted to start here with, it's really section 6. And so section 6 spends some time doing what I'm trying to do now and says, why do we even have quantum mechanics? And I'm going to say it's because of the wave nature. See, the wave nature makes things quantized. It's not so much that it's an electron or that it's small, it's the wave nature. We saw that with the guitar. We saw that with the trombone. We saw that in all of our acoustics. Because acoustics is waves, we get this quantum nature, and so we get the same thing with the atom. And I've said that many times because, again, I think that's one of the most powerful things you guys can take away from your physics education is not only is there quantum mechanics with experimental evidence, but why there is quantum mechanics. Okay, and so your author feels that way too, and that's why he spends a whole section, section 6, explaining it. And again, I started it last lecture, and I'm just going to continue on here. And so say this is his kind of first picture. In fact, I think he gives another picture in this section, if I remember right. Yeah, that's kind of neat to see. He takes that 3 wavelength and also shows you 4 wavelengths. So here is what he's calling R3, because again, thinking of the orbital here, going around, and if it was a particle, you would just say, okay, it goes around right here. But treating it as a wave now, he's going to start here and go, okay, this is one wave, this right here is a second wave, and this right here is a third wave. In fact, he even labels from a crest to a crest and saying this is wavelength number 3. And he's trying to point out that there are many possibilities. There's not just one possibility of 3 wavelengths. 4 wavelengths would work too. And because you're talking about the circumference of a circle, this wavelength number 4 would be different than number 3. Not just because it's a longer wave circumference around, but just because of the nature of I got to get an integer number. And so number 4 right here, and you can kind of see if I start right here, this would be 1 wave, 2 wave, 3 wave, and 4 wave. And so an integer number of wavelengths as you go around. So the radius of number 4 and the wavelength of number 4 are definitely different than number 3. But either way, it's the same piece of physics that I'm going to say an integer number of wavelengths makes the circumference of the circle. Okay? So let's keep this in mind. Again, the reason why we have quantum mechanics. And let's apply some math to our thinking. And this is what your author does in the meat of this chapter. I would call this section 3. Like I said, adding the wavelength in there really might be a step beyond Bohr. But I'll explain that as I kind of go along here. So looking again as what we call the Bohr atom. In fact, I'll even put Bohr atom. And say here, and I'll draw a less than perfect picture. So I'll put a center for the nucleus here. Maybe I'll draw an orbit. And I'll do 1, 2, 3, 4, 5. Hey, that came out better than I thought it would. All right, but again, whether it's 4, like in the picture, or 3, like in the picture, or 5, like I've just drawn, here is what my math is saying. I am saying 2 pi r, so that's the circumference, rolled it around, has to be an integer number of wavelengths. So n can be 1, 2, 3, ... Okay. Well, let me then remind you of last lecture. Last lecture, how's the best way to write this? Oh, I'll put it here, is de Broglie said the momentum is h over the wavelength. Okay? And so if I say, let's put these two together, maybe eliminating the wavelength. So when I combine these, I'll have an equation that talks about its radius and its momentum and its quantum number, but not its wavelength. So solving this for wavelength, I would say wavelength equals to h over the momentum. And putting that into here, so I'd have 2 pi equals, or 2 pi r equals n times h over the momentum. Now maybe I'll write the momentum as mv. I don't know. I debate on whether or not putting that together. But watch this for a moment. If I move either the p or the mv to the other side, so I'll have 2 pi mvr equals to nh. And then maybe if I recognize right here, and this is going to take us way back to Physics 110, this is our angular momentum. This is, I guess, chapter 10, where we did the principle of conservation of angular momentum. And remember, we said angular momentum is the linear momentum times the distance. That's what I have here. And if you remember, we used the symbol L. And so if I solve this for L, I will get nh over 2 pi. Let me pause right there. Because remember, I said that Bohr actually did this problem before thinking of them as waves. And what Bohr did is essentially start right here. Without justification, Bohr said the angular momentum will be quantized. And he looked at some of the experimental evidence and said, well, if we quantize it as Planck's constant divided by 2 pi, things seem to work out just right. Now, when he does that, he doesn't give an explanation of why the angular momentum is quantized. He can't. Until you think of them as waves, you don't have an explanation for why things are quantized. But once you do think of them as waves, now you have that reason why. And so this first step is the part of the Bohr atom that I would say is the modified, where I'm going to start by saying they are waves, and then an integer number, because of constructive and destructive interference, has to equal the circumference. Then when I do the de Broglie wavelength and put it together, I come up with this conclusion that the angular momentum equals something like this. The n And then we like to call this h bar, sometimes referred to as the reduced Planck's constant. And of course, the reason why is Planck's constant divided by 2 pi shows up a lot. And you can imagine when you work with atomic physics, it would show up a lot because, of course, you have the quantized nature, so you have the h, and you also have things going in a circle, so you have the 2 pi floating around. So since they float around a lot, we just kind of group them. They're all constant, so you might as well put the h together with the 2, together with the pi, and call it just one constant and call it Planck's reduced constant. And so h bar is the symbol for that. Now, that's not too important, but I'll say what is important is notice then that the angular momentum is quantized. Because remember then n can be a 1 or a 2 or a 3 or a 4, dot, dot, dot. And so let's keep working with this because everything I'm going to do past this point is going to be valid for the Bohr model because, like I said, when Bohr did it without being the wave nature, he just starts off with this statement that the angular momentum, without justifying it, is equal to an integer number of Planck's reduced constant. And then he does all the math that we're about to do, and he comes up with some amazing results that work out incredibly well. So let's keep going with this, but maybe I will then put a box around this. I won't mess with the reduced Planck's constant, and I'll just say, okay, this is nice to know about the atom, that the angular momentum is quantized 1, 2, 3, 4 times the reduced Planck's constant. Now, what Bohr is actually after is this question. What is the energy in this atom as the electron goes around? Because as we were introduced in the last chapter, we know that if this atom is going to give off light, if it's going to create a photon, and the whole reason we call it a photon is because we know that the atom would be at some energy level, and if it lowers down to a new energy level, because of conservation of energy, it's got to get rid of that energy. And that's where the photon comes from. So the photon is created to preserve conservation of energy as the atom goes from, say, a higher energy level to a lower energy level. Or the other way around can happen too, where a photon comes in and hits an atom and gets absorbed. That's how light gets absorbed, is the photon goes away, the energy's gone. Where does that energy go? Well, it goes into the atom, and so it's got to be quantized. The electron can only go to the next higher state, or the one after that, but the point is it's quantized. So let me continue on here and put together some of the physics that we have been learning for this, whole year. And so going back to our mechanics, the electron going around would have a kinetic energy as 1/2 mv squared. Or you could write it in terms of its wavelength from the last chapter, which would we had h squared over 2m lambda squared. But at this point, since I've eliminated wavelength from my equations, let me think of it more as a particle again. But of course, let me never forget that it's not really a particle. That's how I got this far, to justify why it's quantized. But this would be the kinetic energy of that electron. And then we would have the potential energy sub E. And so that's the beginning of this semester, the electrical potential energy. Now, I hope you kind of remember us working with electrical potential energy. And so here's where we have to go back to our model of the atom. This is why we had that sections 1 and 2. So I have a nucleus, and then I have a charge going around it. And we learned that the potential energy, the electrical potential energy, was equal to Coulomb's constant. Oh, let me not forget the negative. So we had Coulomb's constant. Then we had the electrical charge of the first particle, the electrical charge of the second particle, and then the distance separating them. And so I'm going to put this into here. Okay. So I have a 1/2 mv squared. And then I will, like I said, take some stuff from earlier on in the semester, minus. And so I'm going to put Coulomb's constant. Now let's go back to our picture of the atom. Remember the atom, here are the particles. The first particle, if you will, is, make sure I say this right, the first particle would be the nucleus, okay? And so the nucleus would have a charge of, maybe I'll start simple. Why don't we just start with hydrogen? And this is what Bohr did first. Because as I showed you in that periodic table, the atomic number keeps increasing. And so we will later on say that the nucleus has a charge of 1 electron or 1 proton times Z, its atomic number. But maybe just to keep it a little bit on the simpler side, and I'll come back then and talk about the other atoms. Let's start with hydrogen, because for hydrogen, Z equals 1. And so I won't have to worry about this Z. But I do want to ask, what about the other atoms? But I think it's better just to start with the simplest one. So I'm going to put E for the charge of the proton. So remember, the charge of that proton is that 1.602 times 10 to the minus 19 coulombs. Now, the other particle would be the electron orbiting around. And again, if I pick on hydrogen, there's only one of them, so I'm just going to call it another E. So this becomes an E squared over R. Okay. Let me just put a little box around this for a second. Because like I said, here's Bohr's thinking. It's trying to figure out how much energy would this electron have as it goes around. And so it's going to have some kinetic energy and it's going to have some electrical potential energy. Okay. It's okay. Need to wet my rag a little bit here so I can do a little bit of racing. Now, there's something else going on here. And again, we're going to have to go back to our mechanics way back in, circular stuff. I think that was chapter 6. And so let's put together chapter 6 and then also the first chapter of this semester, which is Coulomb's law as they interact. And that is, if you think about, so here's the nucleus and here's the electron going around. And like I said, I'll just draw it as a particle, even though we started this thinking of them as a wave. But like I said, once we got to this point, we've kind of eliminated any of our wave nature from them. That was just justifying how we had a quantum nature. So going back to the simple Bohr model of this planetary going around, I could say then what is pulling the electron in is the electrical force between the two. Now maybe I should just remind you, because it's been a while since we did the chapter on Coulomb's law. I think it was like chapter 18-ish. And we said if you took Coulomb's constant and then multiplied it by the charge of each of them and the distance squared, see, that was the difference between the potential energy, right? The potential energy only had an R, didn't have an R squared, and it had a negative sign. Which, of course, remember, we got it from this and we integrated it, because the integration of force over a distance is the energy. So again, going back to physics 110. And so these were mathematically connected. And so I'm going to apply it to this case. And so my two charges are the nucleus, which has a charge E for hydrogen, and the electron, which has a charge E. And so then I will take that interaction and I will go all the way back to chapter 6 and say, since it goes in a circle, it must be equal to mv squared over r. Because what we learned in chapter 6 is if you add up all the forces, it has to equal to ma. I guess we learned that in chapter 4. But then in chapter 6, we learned that a was v squared over r towards the center of the circle. Now, doing that, you can see that one of the r's would cancel. And you have a nice little equation here that could be grouped together with this equation. And you might be able then to think about these terms, and it turns out that they become like terms. fact, you can actually see right here this term, 1/2 mv squared. See that mv squared? That's what I have right here. So keeping that in mind, I'm going to try this. I am going to then put, maybe, no, no, let me not do that. My bad. I guess I could. Let me hold off because I'm just thinking in my mind I might make the math harder that way. Okay, so let me pause for a second and just write this as, and I can debate here how to write it. Well, let me leave it alone for a moment, because there is quite a bit of math here, and I don't want to make it harder than necessary. Let me put it around here. But as I was beginning to say, I could solve for some parameter here, and it could be either a V or an R. That's what I didn't say, it could be an R and put it into here. But I also want to put it with this one. And so it's these three equations that I want to put together. And remember, when you put two equations together, you eliminate a variable. And so I would like to see the following. I would like to have an equation for the energy. So I want to focus on here. But it would be nice if it didn't have a V or didn't have an R in it. And so let's go ahead and write this one out again. Remember, this L is mvr. And then this would be N times Planck's constant over 2 pi. And since this has both an R and a V in it, I'm kind of thinking maybe what I should do is solve maybe this one for R and put it into here and here. And then I would have equations that only have V's, and then I can put that together and eliminate it. Yeah, I think that's the approach to go, I think. Yeah. Because I think if I'm looking ahead at what might be the easiest thing to do, and I see this mv squared, and when I bring the r to the other side, I have something that looks a little bit like this, except it's got an extra v in it. And so maybe I will put a v over here, just one of them. And then realize that the group together, and that's how I was saying, I was kind of looking for a way to help my math here. MVR, I can write that as NH over 2 pi. And then that way, I can put this and solve for V and put it here. Oh shoot, I still got to get rid of the R. Okay, never mind, that was my bad. I'm not sure I like that now. Okay, so let me just do it, I'll call it the most direct way here. All right, let me go ahead and just solve this, which I hope doesn't turn out to be too hard. I didn't want to take too much time here. But let me just say, here is the R. And so the R would become an NH2 pi over MV. And let me put that then into here. So this would be a K pi. And right here over R would be an NH over 2 pi MV equals an MV squared. You could flip and put this up here, so it's 2 pi MV. So cross that out. I guess I would also then cross out here an M and a V, so an M and a V. And so I would have V equals, and so it looks like I have a 2 pi here. I have a K, I have an E squared, and I have an H and an N. That didn't look very good. N and an H. Okay? And so this is kind of nice because it tells me what V is, which I'm going to put right here. But I'm also going to put in my R. But maybe before I do that, I'm going to then put right here that V. So this is a 2 pi, a K, an E squared flip, and then there is an N and an H. So there's my R without any kind of V in it. So there's my, as I said, my R without any V's in it, and there's my V's without any R's in it. So if I put it into here, and so let me go ahead. I told you there was a little bit of math here, and so I probably should have maybe skipped a couple of these steps here. But here is E, and so I'll have 1/2 M, and so right here would be V squared. All right, so let me square all that. So that would be a 4 and a pi squared. It would be a K squared, and it would be an E to the 4th. I think that's right, a K squared E to the 4th. And then all of this would be over N squared H squared. So that's that first term. Let me then subtract, and so I've got my Coulomb's constant and my E squared, this R. And so it would be the reciprocal of this R. So putting the R, I would have an N squared and an H squared. Oh, let me pause right there. See the common denominator right here? Okay. And then when I flip this, I will have a 4 pi squared. Okay, so there's the 4, there's the pi squared. I will have a K and an M and an E squared. So for the K, I'll just square that. For the E squared, I'll make that a 4. So let's see, K, E4, and then my M. And if I did all this right, surprisingly, after all of this, those are actually identical terms. Let's see, it looks like I've got a 4 pi squared, a K squared, an E to the 4th, and an M. And of course, this right here is a plus 1/2, and this right here is a minus 1. So it comes out to be minus 1/2. And then I've got the 4 pi squared, K squared, E to the 4th, M. All right, well, since that took me a little longer in terms of math than I was really anticipating, let me not take the time to put in all the numbers. I'll leave that for your fun. But if you put in all of these numbers, the 1/2, the 4, the pi squared, remember Coulomb's constant, 9 times 10 to the 9th. The charge of the electron, 1.602 times 10 to the minus 19. The mass of the electron, 9.11 times 10 to the negative 31. H squared, 6.63 times 10 to the minus 34. If you do all that, you, of course, will get units of energy. And in the units I just said, they would be joules. Convert the joules to electron volts, and you get what I'm after here, which is a very useful, powerful equation that says the energy is quantized. That is looking at the energy in this model of the atom, the Bohr model. Like I said, it's not as perfect because it's not three-dimensional, but at least it's a little bit of quantum mechanics because we put the wave nature in there. You get this very famous equation. And now that we worked it all out, I guess the good news for you is don't bother to work it all out ever again. Your author does it in section 3. I just did it for you. But your author does want you to see that this then does lead to a quantum of the energy. And so let's talk a little bit more about this. And so I can have some room to work with, I'm going to put that equation right here. And so I'll say it again. If we think about our electron being a wave, and with the constructive and destructive interference, it has to be an integer number of wavelengths around. And if we put all that together with all the other stuff like our kinetic energy, our electrical potential energy, our electrical forces, our centripetal acceleration, all those things that I put together here, we come up with a formula that has this quantum number. Now remember, n can be 1, 2, 3, ... times this negative 13.6 electron volts. Now, if you also remember, in order to make it a little easier, and you can see it was still kind of a lot of math there, I said, let's just take the atomic number z equal to 1. Because what if I hadn't done that? Well, then I would have a z floating around. And then, of course, you saw that things got squared. And it turns out that if we had put a z in there for the atomic number, you would get a z squared. Which, of course, if it's hydrogen, you would just put a 1 there, and so you would have the same equation that I have right here. So this is the equation we would use for hydrogen. But if we went on to helium, helium being the second one in the periodic table, I would put z equal to 2. Or lithium, then I'd put z equal to 3. Or a real interesting and important one for you guys is tungsten, because the tungsten is used as the atom to generate X-rays for all this, broken arm stuff, and any of you go into medicine, or even if you're just in the research of the physical science, that Z is so high, that the energy is so high that we make really high energy photons, and they're in the X-ray region. And so these X-ray machines have tungsten as their main source of creating the X-rays. And so for you guys, I want to make sure I throw that Z in there. Now, in terms of the science, I think if we just continue to talk about the simple one, the hydrogen, it'll begin to make more sense to you. Now, what I'm going to do then is say, what if I were to draw an energy diagram for this? And so I'm going to just put E here and say, all right, if we were to put in n equal to 1 here, and we were to say we're talking about hydrogen, so Z is 1, in other words, this equation here, I guess I would say then this lowest energy that the atom can have is a negative 13.6 electron volts. Now, I hope the negative makes sense to you, because remember when we were doing our electrical charges, we said if you had enough energy to pull it apart, according to that equation of potential energy, that would be 0. So the atom is not completely pulled apart. The atom is actually together. In other words, the electron is actually captured by the nucleus. So it must be at an energy lower than 0. And so 0, I think, kind of confuses students. They want to think of it like back when we did mechanics and say, oh, take the lowest point to be 0. But remember, we had that choice. So if we took a midpoint as 0, things lower than that would have negative, and things faster than that or above that would have positive. And that's essentially what we're doing here with our electrical charges. We're saying that if you separate them infinitely far apart, but with no kinetic energy, then that's our zero energy, because it had zero kinetic and zero potential. So anything that is closer would have negative potential energy, but of course if it's moving, then it has positive kinetic. So when you combine the two, it may or may not come out to be negative. And you can see in this one it comes out to be negative, and that's just a fancy way of saying that even though it's spinning around and has a significant amount of kinetic energy, it's not enough to overcome the negative potential energy, and so it's not moving fast enough to fly away. Something that would fly away means not only did it get far away, so its potential energy is zero, but it's still moving, so it has positive kinetic energies. So if you're talking about an atom with positive energy, that means it's not bound, it's not hooked together. It means it was spinning so fast that enough kinetic energy it could leave. Of course it slows down, but it gets really far away and it's still moving. And that's why it can get far away, because it had so much kinetic energy. And so the zero energy sounds kind of funny, I know that, but it's very useful. It just says that anytime we have a negative energy, it's bound together. And granted, it's a little annoying at times to use negative energies, but I just want to say there's nothing wrong with that. We just tried to avoid it when we did our mechanics by calling the lowest point zero. But if you called the middle point zero, then things were down here, they would have negative energy, and then they went up here, they would have positive energy, and that's exactly what we're doing with the atom. It's just better that way. It sounds funny, but it's better that way to have some negative energies along with some positive energies, and so zero is kind of this middle ground. So I say all that because then way up here would be zero energy. And I know it sounds really funny. That way up here, all of this energy would be zero. All of this energy is when it is free. However, for those of you who've taken chemistry, you've probably done this number a lot. You call it the ionization number. You say, okay, how much energy would it take to take the electron completely off and completely free from the hydrogen atom? Okay, so now that we just did the math, I would say, well, if you're going to take it completely free, the potential energy would be zero. And if it's still moving, you'd have something positive. But let's just say it's the minimum. So the minimum is you got to break it all the way free, and then it's barely moving. So let's just say the kinetic energy is zero. So the total energy would be zero. That's why we like that. So if you are down here at negative 13.6, you have to give it 13.6 worth electron volts worth of energy in order to break it free. So what we say is we say the ionization energy of hydrogen is 13.6. That's what the math just said. The math just said if it is in its lowest state and you want to give it energy, enough energy to break it free, in other words, enough energy to get to zero, you got to give it 13.6. So we say the ionization energy of hydrogen is 13.6. And that's a number that you probably saw quite a bit for those of you who've done chemistry. This is where it comes from. Actually, it probably comes from measurements first, and then, hey, now we can mathematically explain it. And that's the beauty of the Bohr model. The Bohr model actually is then giving you the correct numbers that we get from the laboratory. So that's pretty cool. Now, maybe I'll grab my calculator here, because if I pick n equal to 2, and so maybe I'll put n equal 1, and I put here something like n equal to 2, I would get 13.6 divided by 2 squared. And maybe on my graph, I should even make it a little bit higher. In fact, in a moment, I'll turn to your textbook, because your author does this graph and does it with a scale factor that is much nicer than what I'm doing. But this comes out to be, whoops, let me put it right here, 3.4 electron, negative 3.4. And so that would be the next energy level. But here's the main point. What if the electron was at this point? And if you asked, like I was asking before, how much more energy would you have to get it to break it free? Well, then it would only be 3.4. But on the other hand, if you left it alone, it would want to go back to a lower energy level, and it's this difference I'll call it delta E, that's got to go somewhere. That is then the energy of the photon that would be emitted from this hydrogen atom as it changes from level number 2 down to level number 1. And I'll put one more up here and then I'll go to your book here, but level number 3 would, I guess, be 13.6, negative 13.6, divided by 3 squared, which is 9, would be a negative 1.51 electron volts. And so I'm going to say the same thing if the electron was in this state. So somehow you already gave it energy. We'll call it the excited state. And so 3 means it would have 3 wavelengths around the circle. And it wants to lose that energy and become 2 wavelengths around the circle. So it wants to go from 3 to 2. We would kind of draw this and say, hey, the electron is going to change its wave pattern. It's going to go from 3 down to 2. And that means there is a change of energy. Call it delta E. And maybe to be clear, I would put delta E on down here 2 to 1, but this would be 3 to 2. And that would be the energy of the photon. And clearly that's a different energy than this one. So this hydrogen atom would give a photon that's different. And usually when we have a bunch of hydrogen atoms that we try to get excited, some of them get excited into level 2, and then of course they tumble down to number 1. And some of them get excited to number 3 and tumble down to number 2. And the ones that went to number 2 then go to number 1, and then that would be that same photon. Some of them even do this. Some of them go all the way from number 3 down to number 1. And so the energy of that photon, delta E, would be more energy than any of the others. And so it'd be 3 to 1. My point is, even though the energy is quantized, there's quite a few different transitions that correspond to quite a few different energies, which would then correspond to quite a few different wavelengths. And so the wavelengths that come out of this hydrogen gas that I got excited would actually be quite a few. Now, they would be quantized, but they would be quite a few. Let me show you a picture here that I think your author does better than I just did. And maybe I should scroll on a smaller setting, because I think this is all the way back to all the math he did in section 3. And it's the math that I just did. So I think that's section 4. This is what I'm looking for. Let's see if it's useful here. Yeah, maybe I'll start here. Okay, so starting here, your author does, like I said, a little better job with his energy diagram than I did, where he says, okay, so here is the lowest energy that this atom could have, right here, n equal 1. Now he doesn't put any numbers here, so maybe that's not good, but then he says number 2, and then number 3, and then number 4, and then number 5 here. And he goes on up, but then he shows what I was trying to show, that maybe an atom would be up here in number 4, and it would lose some energy and go to number 2. Now, that's not the only option, and that's what I want to emphasize. Your author doesn't show it here, but it could have gone from 4 to number 3, and that would have been a different photon of a different wavelength. But it also could have gone to 4 to number 2. And again, when you have a container of hydrogen gas, one atom is probably going 4 to 3, but another one is going 4 to 2. So you get both of those at the same time. Now, they don't come from the same atom, and I want to emphasize that. Clearly, there's only one option for one atom. But there's a lot of atoms in here. And so if you just put a gas of them and you put up a spectroscope, you're going to see the wavelength for the one that corresponds from 4 to 3, as well as the one that corresponds from 4 to 2, as well as the one that corresponds to 4 to 1. And then, of course, the one that went from 4 to 3 could then go 3 to 2. So you're going to see that one. But you could also see the one that went 3 to 1. Or you could see the one that goes from 2 to 1. And so let's see, how many options do we have there? That's 6 options. And so just because we got into level 4, we've got 6 different colors that we could see. Now, that doesn't mean they're all in the visible spectrum, by the way. But it does correspond to putting what we've learned in the past together and really understanding the physics of the atom. And I'll say it again, that's the whole point of this chapter, atomic physics. Why does the atom behave the way it does? Why does it give off these particular wavelengths that it does? Well, the other picture, like I said, that I think your author does better than me, is kind of then showing all the combinations here. And this might be just a little too big to fit on the screen. Still a little bigger. How about 150? Okay. But your author kind of says here that look at all these combinations. And they have special names. And basically anything that starts at a higher level and drops down to level 1 is the Lyman series. And that's going to be a lot of energy. We'll run some numbers in here, but you'll see that this energy is so much that they're all at higher energies than even violet. So we wouldn't see any of these with our eyes, but they're there. And you can measure them with fancy equipment. And so we have what we call 1 series. It's the Lyman series. Now, the Bohr series is the one, or at least some of them, are the ones that are in the visible spectrum. And so from any of the higher levels, like 3, 4, 5, and 6, coming down to number 2 means that they would give off a wavelength of, and again, let's do some numbers here in a moment, but those are the ones that would be in the visible spectrum, at least up to a certain level. And so 3 to 2 is kind of in the red, and 4 to 2 is kind of a turquoise. 5 to 2 is getting out to a high blue or a violet. 6 to 2, you can see that one, but barely. 7 to 2 then is too much energy. Now we've gone into the UV. So you don't see the whole Bohr series. But you can see as you get to higher quantum numbers and they come down to number 2, it's going to be more and more energy. And then again, that's why the Lyman series, just the lowest energy one, from 2 to 1 would be the lowest energy. That would be so much that you wouldn't even see it in the visible spectrum. So that's why 3 to 1 and 4 to 1 and 5 to 1, all of those are even more out of the visible range. So again, you wouldn't see any in the Lyman, and you're only going to see the first 4 with your visible eyes in the Bohr series. And of course, then anything that is above 3 and tumbling to 3, so like 4 to 3, 5 to 3, 6 to 3, this Paschen series is also another one. And it turns out that even the most energetic one isn't enough energy to be in the visible. Those are all infrared. So you wouldn't see any of those. But I do want to point out of how many different combinations we could have. And so even though the energy is not continuous, which means we can't have all the different colors and all the different frequencies, there still is a lot on here. I guess technically infinite, because n can go up to infinity. But of course they get closer together, and you know, but the idea here is that there is a lot. You might even call it infinite, but it's not continuous. It's quantized. And that's the whole idea here of these pictures here. Okay, well, maybe I will use this then as a chance to say, maybe we should try a calculation or two. Well, let's take advantage of all this work we now did. And so with this equation that we have for the energy, coupled together with what we learned last chapter, where they would jump from one quantum state to another, which, by the way, I think that word quantum jump is misinterpreted. And so I guess I'm not a big fan of quantum jump, because it makes it sound like the electron is going from one place to another. And it's, I mean, when you use the word jump, that's kind of what you mean. You jump from one physical spot to another physical spot. And that doesn't describe really well what's going on with this atom. This atom is going from one wave pattern to another wave pattern. It would be a lot like if I had a beaker filled with water and I was shaking it, I might have a wave pattern. And then if I shook it a little less vigorously, I'd get a different wave pattern. But remember, the wave pattern is the electron. The electron didn't change. It's still there on the surface of the water. Its pattern just changed, which means the energy it has changed. And so it is a quantum jump in energy, but it's not a quantum jump in physical space. And that's why I think the word jump is wrong. It should, I don't know what would be a better word. It should be a quantum transformation. It changes from one pattern to another pattern. The electron doesn't change its position. It doesn't just magically go from point A to point B, as you can sometimes see in the sci-fi movies. In fact, I'm remembering an old TV show which was called Quantum Leap or Quantum Jump, something like that. I think it was Quantum Leap. And if this was a leap in time, not space, and so they'd be in one place and then jump to another. But again, that's just a poor representation. We're not saying the electron jumps in space or in time. It's a jump in energy. It's a change in wave pattern. Just like shaking a beaker vigorously and it's got one wave pattern, and then less vigorously, and it's got another wave pattern. It's just a different amount of energy. The energy changed, and the energy went somewhere. It went to the photon. And that's what I want to calculate here. So let's give this a try. Let's calculate then the energy. And so let's do something like this. Well, I'll leave it in general at first. Let's just say that we are at some initial level here, N1, or N sub I, and we go to some other level, NF. And so if I looked at the change in energy of the atom, I guess I would go, okay, what is the final state minus the initial state? That would be the change of energy of that atom. And so using the formula we just derived, it would be negative 13.6 electron volts and N final squared. So if we went down to n equal 1, that's what I'd put right here. That'd be the Lyman series. If it went down to n equal 2, that would be the Balmer series. So then minus a negative 13.6 electron volts, and then the initial. Okay. And again, this would be the change in energy of the atom. And I want to be careful there, because the atom is losing energy. And this then should be a negative number. I mean, maybe you'll see it here. Let's just say, for the sake of conversation, it starts, and so right here, it has an initial energy of n equal 2. Which we calculated earlier to be this negative 3.4. So this would be minus the energy, which is negative 3.4 electron volts. And of course it would finish, let's say, in state 1. And so as we calculated, and that's an easy one, it would be a negative 13.6 electron volts. And that would be the change in energy of the atom. And you can see then the two negatives, of course, become a positive, and you can see this overall result is a negative. And then that's a good sign. The atom loses energy. So I'm going to take a negative 13.6 and add to it 3.4 and get a negative 10.2 electron volts. So again, if this electron were to take this quantum transformation, jump, leap, whatever you want to call it, and it would go from energy level 2 down to energy level 1, the atom would now have lost 10.2 electron volts. Okay? But that negative energy, that loss of energy, goes somewhere. And as we saw in the last discussion, last lecture, and what I'm trying to emphasize now is, where does it go? It goes to the photon. And so I would say this: the energy then of the photon must be the opposite of the change of energy of the atom. And I really want to emphasize that negative, because this tends to confuse students, that sometimes we have the negative and sometimes we don't. Why do we drop it? And again, it's the principle of conservation of energy. If the atom lost the energy, and so I want to remind you, this is the equation of the energy that the atom has. And I'm trying to find then, say, the wavelength that the photon has. I need to take the energy that is lost by the atom, take the opposite of that to say what is then gained by the photon. And so that extra negative can confuse students. So I would say this, that the energy now of the photon is a plus 10.2 electron volts. And that's how I get a plus sign out of this. Okay, now if we go back to last lecture, we know that the energy of a photon is hc over lambda. And remember that hc, a very convenient number, is the 1240 electron volts times nanometers divided by its wavelength. And so if you're working with energies in electron volts, which we are, and you want to solve for maybe wavelengths in nanometers, which I think I do. It's kind of nice to talk about wavelength in terms of visible light, so in terms of nanometers. This is a really convenient number. So let me put the 10.2 electron volts for the energy of the photon. Let me put the 1240 electron volts nanometer. And let me then answer what the wavelength would be for this transition of 2 to 1, which I would call it the first term in the Lyman series we were just looking at. And so I will take my 1240 and divide it by 10.2 and get a 121.6 nanometers. And I'll just remind you that the visible spectrum is the 400 to 700 nanometers. And clearly then this is much smaller than that. And so this is out in the ultraviolet, even the far ultraviolet. I wouldn't say quite getting to X-rays, but it is ultraviolet B, not ultraviolet A. It's way out there. Okay, now remember this also, that this would be the smallest energy in the Lyman series. So remember, the transition from 2 to 1 is what I just calculated. If I looked at a transition of 3 to 1 or 4 to 1, I would have even more energy, which of course would make this number bigger, which is going to be a corresponding wavelength even smaller. So as I said when I was showing you the author's picture, you're not going to see this 2 to 1 transition with your eyes. This would take special equipment that can measure ultraviolet light. And the other ones would even be more ultraviolet, maybe even getting borderline X-rays as we got higher and higher. In fact, I guess the most we would ever get would be 13.6 electron volts as we went from way up here n equal infinity down to here, 13.6. I don't think anybody would classify that quite yet as X-rays. Maybe, not sure where the transition, we should go back to that little chart. But regardless of where it is on the chart, I did want to point out that it would not be seen with your eyes. And that's what I was saying earlier, that the Lyman series is there, but we're not going to see it with our eyes. Hopefully I'll be able to show you a few of them. All right, let's do another calculation. Let's be a little more general this time. Let me erase this. And kind of come back to this step right here. And so on this step here, let me just leave it at, okay, where does it land after, where does it start? So this is the initial quantum number that it's in, and it goes to the final one. Okay. That is the change of the atom. I do want to remind you that the energy then of the photon is negative of the energy change of the atom. Okay. So, if I take the opposite of this right here becomes a plus 13.6 electron volts over n final squared. And then the opposite of this is then minus 13.6 electron volts. And of course, when I did it, I put in, let's see, did I say that right? I put in a 2 here. No, it landed on 1. And I put a 2 here. Yeah, and I got a positive number for the photon energy. And so I like to write this in terms of the photon energy. But sometimes that confuses students because they think, well, didn't you write this backwards? And I would say, well, it's backwards if you're talking about the energy of the atom, but it is, of course, the energy of the photon that I'm talking about. In fact, I could even go one step further and replace this with hc over lambda, then equals to 13.6 electron volts, and then final squared, minus 13.6 electron volts over initial squared. I could even take this one step further and replace this, remember, with 1,240 electron volts over nanometers. And then this would give me a nice general equation to say I could probably quickly calculate the transitional or the energy from different states. And so let me do the first one in the Bohr series. Remember, the Bohr series was terminating at n equal 2. So the first one would be a 3 to a 2. And if you remember me saying then, that one actually has the energy that's somewhere kind of in the red part of the visible spectrum. So let's see what a calculation gives me. And so using this idea right here, I'm going to go 13.6 divided by its final state. And so we're gonna land at a 2. So I'm going to divide that by 4. Then I'm going to subtract 13.6 over its initial. So that'd be 3 squared, or a 9. So again, I'm looking at a transition of state 3 down to state 2. What's its wavelength? Okay, well, let me just hit enter for that. And so that's this side of the equation. And then, of course, let me remind you that this is 1,240, so I'll bring it over. So divide by 1,240. That then is the reciprocal of the wavelength. So let me take the reciprocal. And I get a wavelength of 656 nanometers. And so, like I said, that's in the visible range, and it's getting close to that blood red of 700, and so it's a dark red. Maybe still kind of a red. Maybe I wouldn't call it a blood red quite yet, but it's not that close to 700. See, but I can keep doing this for the Bohr series. I could say, what would a 4 to 2 get me? And so over here, I'll just go 13.6 divided by 4 minus 13.6 divided by, and I will be starting at 4, so 4 squared is 16. Then I will divide that by 1,240, and then I'll hit the reciprocal, and I will get kind of a turquoise color at 486 nanometers. And then I can do a 5 to 2, the same thing. So 13.6 divided by 4 minus 13.6 divided by 25, all of that divided by 1,240, taking the reciprocal. And now we are getting very close to the edge of the visible spectrum. This would be a violet one. Let's look at 6 to 2. Makes me think if I'll even be able to see it, it'll be out of the visible. But it should be a shorter wavelength. Now it turns out that it is a little bit under the 400. I mean, let's give this one a try here. But 13.6 divided by 4 minus 13.6 divided by 36. then divided by 1240 and reciprocal. And this is actually technically still in the visible range, but like I said, when we actually try this in lab, and I'll try to show you here on the video, this is not going to be really observable. First of all, these are close together, so they kind of blur. And second of all, they're both violet, so all the reason more, it's hard to tell that there's two of them. But this is right at the edge of your spectrum, and so your eyes are very insensitive to that. And so we say you can see it, but it's really hard. And especially with what I'm going to try to show you in the camera in the lab, our equipment's not that great, and it just doesn't come out that well. However, I'll stop there because I want to keep going with other things. But I just wanted to emphasize here that you now have this great recipe for figuring out the wavelength as the electron tumbles, if you will, from one level down to another. Now, there's probably one more thing I should say, which I think your author covers it in section 4. Yeah, so I guess what I've been doing is section 3. But in section 4, he just simply says, you know what? Everything we did was with atomic number equal to 1. What would happen with that extra factor of z? And so let me take a different color and come back over to here and say, well, there would be this z squared. And so if you follow that through, all of this then would be multiplied by z squared. And so I'll go ahead and put here a z squared and say, all right, what if we wanted to do this problem with tungsten? And like I said, your author tends to focus a lot on the tungsten for reasons that they make really, really high energy photons, really, really small wavelengths, and they're used for our X-ray machines in our medical field. And so doing this, of course I could do this for any then element, but not just tungsten. I think tungsten is 74, okay. Although you also want to be a little careful, even though tungsten is 74, maybe I should do an example with tungsten, because it's probably best to do a 73. Even though the number is 74, well, what will happen is the electron will tumble all the way down to that first orbit, but there'll already be an electron in there. And that one electron kind of balances off one of the protons. So technically there's 74 in there, but there's an equivalent of 73. And so it's shielded, if you will, by that one electron. And so taking that into consideration, it's probably more appropriate to say it's the effective z number, not the real z number. All right, but that just reminds me that after the break, I really should find a good example with tungsten and do that one with you. But like I said, your author does do this. In fact, he's got kind of the same energy chart, and so it doesn't look too much different. He just calls this up, and so let me scroll on through where he gets into tungsten here. Yeah, and he says, okay, let's watch the transition. And so you kind of see the same energy diagram. All that has done has been multiplied by that z squared. You can see here then that he labels it k, or n equal to 1, and l, and n equal to 2, and m, and n equal to 3. And so which shell is it? That's because we like to call our X-rays either K X-rays or L X-rays, because if the transition is from something higher down to the first quantum number, the K orbital, we call these K X-rays. But if it is tumbling from something higher down to the L, we call them L X-rays. And so it would be the equivalent of the Lyman series and the Balmer series and the Paschen series. He doesn't show it, but there would be an M series also for our X-rays, and that would be equivalent to the Paschen series. So that's something that I probably should point out. In fact, he then, And since you guys are here in the life science, it's kind of nice to see these high energy X-rays, because the neat thing about X-rays is they don't get absorbed by soft material, but they do get absorbed or bounced off from hard materials. And so that way they can go right through the soft tissues like the skin and the muscle and the ligaments, and then they hit things like bone or teeth or whatever this is in the X-ray here. I don't know if that's in the chest or something sitting in a pocket above it. X-ray image of a person showing the details and an artificial pacemaker. So this person has it in the chest. It's actually on the heart, giving an electrical pulse, making a pulse. So when you took this X-ray, that's what you see. You see the pacemaker. You also see the rib cage and the collarbone and the spine, and anyways. The teeth, again, you can see the teeth, the shape of the teeth. You can see where the teeth are hollowed out. You can see all the cavities, or the cavities have been filled in. They're kind of a harder, darker material, so they kind of stand out. But again, these high energy X-rays go right through, as we talked about. Well, I think that's all that probably really needs to be said in section 4, because like I said, it's really kind of a one in the same, and so I'll kind of leave it at that. But I do want to then keep coming down here before I jump off to some examples. We'll take our break here first. But did he start section 5? Because what I wanted to say last is at the beginning I said, yeah, read section 5. I think this will do really good for your long-term education. There aren't any more equations, and not too much I could really test you on, and you guys have worked so hard already. It's time just to focus on the physics of it. But the application of it, I think, is what you really will enjoy seeing, and the reason why you are required here to take physics. And so if you've plowed through this class this far, you're probably near exhaustion on it and asking yourself, why do I have to take this physics? But I hope along the way you begin to see why. You begin to see, to understand how the X-rays work, and how they're generated, and to understand all this thing that's related to the life sciences. I really got to understand a lot. Going back to osmosis pressure way back in physics 110, or the problems we did with the endoskeleton and how much strength the bicep has to have even though it's reaching a small amount. All right, well, I've talked a lot. It's probably just to say, hey, why don't we take our 15-minute break here, and we'll come back and do some example calculations. Even though I've done a few, I'll do a few more, and then we'll call it a wrap. Okay, let me circle around and shut the camera down. Oh, you know what I should do? No. Okay, I know I've done a lot, but worth one more thing. I told you I would try to show this on the camera. All right, so let me come back here, because this is not going to be easy to see with the camera here. But I practiced, and I think it can be done. Let me take the hydrogen, and I'm going to set this up and blast some electricity through it. And we might have to hope for a good white balance here. I'm going to turn off the lights here in a second. But if you remember going back to our optics, we had these diffraction glasses that would spread the different colors out so we can see them. And so as you're looking at this right now, you're probably seeing kind of a pinkish color. And remember, this is hydrogen, and so just those 4 from the Balmer series that we just calculated are right here behind. I'll bring them back up. But these 4 are coming to your camera right now and mixing with your eyes, and hopefully the color doesn't get distorted by converting into electronic signal and then displayed on your screen. But it should look kind of pink, and because it looks kind of pink, it's the blending of these 4 colors. Even though all those other ones are there, like I said, those wouldn't get absorbed by your eye. Some of them would never even get out of the glass tube. Those higher ones from the Lyman series, the ultraviolet, never would get out of this glass tube. And so that's why this glass tube is going to be really hot when I take it apart. Also, the infrared ones won't get into the camera and get recorded, although some of these cameras go far into the infrared, but they won't get played back because there's just no mechanism in a video file to record infrared. Anyways, all of that is to say, I'm going to put these diffraction glasses in front of that video camera. And as you learned, the light would come out and diffract, and so I might have to move the camera a little bit, but I'm hoping you will see these 4 colors. And with the autofocus, hopefully they won't be too blurry. And so, like I said, I was playing with it and I was kind of impressed. They were blurry, but since I'm only looking at colors and positions, it won't matter. You will see that the shorter wavelength, as we talked about in our optics, would be closer in and a closer angle. Remember that d sine theta equals an integer number of wavelengths from our optics? That's what I'm using here, these fancy diffraction glasses that we did in our optics. And so the smaller wavelength ones, and so the violet ones will be like right here on the camera, and then the turquoise one will be right about here, and then the red one will be right about here. Okay, so I'm going to grab these. I'm also going to turn on a little flashlight because, so you guys can see it better. I'm going to turn off the room lights, but I got to go to this side of the room to turn off the room lights. And then I'll have to walk up behind the camera. Okay, and I just don't want to trip over anything. And, ooh. Hang on, looking at the camera, I see that our display is putting out a little bit of light. So I'm going to turn those off. Okay, and circle back around to our camera. Okay, so on our camera, you are looking at this display. Let me see if I can put the diffraction glasses in front, and then move over a little bit. Good. And I can see it. In fact, since I'm back here anyways, why don't I take this as an opportunity to zoom a little bit. There we go. And I'll do the same thing. I'll put the diffraction glasses here. And I'll have to probably scan a little bit further. There it is. So there's the violet one. There's the turquoise. Oh, and there comes the red way over there. Nice. At least I hope it's nice. This is kind of a small screen here. But there's the four. And you probably can't tell. I certainly can't tell on this little screen that violet one is actually 2 in there. But like I said, that's kind of hard to tell. Okay, now, as long as I've done that much, and if you're still hanging with me, let me come over here so I can see things a little better. Let me turn on a little bit of room lights. But it would probably be worth effort to then, let's look at some other gases that have a higher atomic number. And so this is pretty warm. Let me set that bulb off to the side. Let's go one step up and do some helium. And so helium would have atomic number of 2 and would have a Z in there of 2. And so let me turn that one on. And that kind of has a little peach color. Now, let's not take the time to do a bunch of calculations. But I think that because of the extra electrons and the different places it can bounce to, there turns out to be 7 or 8 or 9 that are in the visible spectrum. But I should have pointed out that notice how then the light, the photons are quantized. And you'll see it again, although there'll be more of them in the visible spectrum, there'll still be a unique pattern. Okay, so let me swing around here, turn off the lights, go back here to the camera, and put the diffraction glasses in front of what, hopefully, if the color balance is okay, that's pretty bright in a dark room, so I don't think the color balance will probably show the, I'll call that a peach color, and maybe when the room lights were on, the white balance showed it better. But I'm going to go ahead and then put the diffraction glasses in there and then scan over. There they are. And so it looks like the violet one is kind of wide. Is that 2 in there? I'll have to look on that on a big screen. But 1, 2, 3, and then a green one, and a yellow one, and a red one. And the yellow one is quite fascinating because it's really quite bright. Got to get everything aligned just right to see some of those other light blue ones. There we go. And I don't get them all on the screen at the same time. But you can see how they're quantized. And that's, again, what I wanted to show you is that, hey, this is quantized. And so this explains a very important piece of physics that, wasn't explained until the discovery of quantum mechanics, that why is the spectrum the way it is? And why are they just kind of set frequencies and not a whole continuum? And so that bothered the early scientists. But with the development of quantum mechanics, as I said, the reason for the quantum mechanics, hopefully you get from the wave nature, we now have an answer to that. By the way, I should point out, and your author talks about it in that section 5 that I hope you will read about, is this gives us a way to uniquely identify elements and compounds without actually touching them. And so if we wanted to know, say, what was on the sun, we don't necessarily have to go to the sun and do a chemical analysis. We don't have to land on the sun and scoop up, which of course is a good thing because the surface of the sun, you're not exactly going to land on. It's really, really hot. And some people joke with me and say, well, sure, you can land on it at night. Okay, silly joke, but actually kind of funny. But the only way we know, like there's oxygen or sodium in the sun, is because of the unique shape, the unique pattern. Sometimes we call it the fingerprint of that element. And so if you look up at the sun and you see this particular pattern, you're like, oh my gosh, that must be sodium. And in fact, by the way, you will notice that this pattern is coming from the helium I said about. And helium is named for Helium, the god of Helios, is it Greek or Roman? Well, one of the two. Helios is the god of the sun. And the whole reason the scientists called it helium is because they actually, interested enough, discovered helium first on the sun. They were looking at the spectrum and they saw exactly what you just saw. They saw the spectrum of helium and they go, we've never seen that on Earth before. What element is that? And of course they hunted around for a while and they came to the conclusion that this is an element that does not exist on the Earth, and so hence the name helium. Now, as you know, it turns out that we have plenty of helium on Earth, we just didn't know where it is. And helium being one of the noble gases, for those of you who took chemistry, know that it doesn't react very well with anything. And so because it doesn't react, it's always a gas, and it's such a light gas, it floats out of the atmosphere. So where do you get helium was like, well, it's not in the minerals because it doesn't react with anything, so it's not in the soil or the ground, and anything that was in the air has left, and so you can see why the early scientists never found any helium. However, it does dissolve in oil, and so it gets trapped in oil. And so once we started drilling for oil and started pulling oil out and separating the gases. A lot of gases are in the oil, including methane. That's how you get, your natural gas, and you separate and you clean it. They found the helium. And so we've got plenty of helium, or at least a lot of helium. I don't know about plenty. And it comes out of the petroleum industry here. Well, let me do one more and even go to something more complicated. So here I grabbed a gas of neon, and neon has number 10. And so if you thought you saw a lot of colors with the helium, which I forgot to count, so maybe it was 7. You're going to see a lot more in the visible, because there's so many more electrons able to transition to so many different levels. Plus, they all get kind of squeezed in a different pattern because of that Z squared. It just has its unique fingerprint. And that was my point earlier on, that you get a unique fingerprint. And as long as the lights are still on, hopefully the camera is giving you a good white balance and showing you that this is kind of a fiery orange color. It's got the warm colors. And when I put the spectral glasses up there, the diffraction glasses, you'll see that the transition here are in the warm colors. There's a lot of red, there's a lot of orange, there's a lot of yellow, there's a lot, even green, but not blue. And so you don't have that end of the spectrum. And so that's why when they all come to your eyes and they blend together, you begin to see, kind of these warm color, because that's all that's really there. But there's a lot of these warm colors. All right, let me circle around again. I'll shut off the room lights. And of course, like I said, it's probably going to totally mess up the color balance, but once I separate it out, I'm kind of hoping the colors come across once they diffract, but a direct shot at the light is a little too bright, and it probably just looks white on your screen. All right, so I'm going to put the diffraction glasses somewhere in here. Oh shoot, I just remembered all that talking I was doing up front. It was zoomed in. You probably didn't see much of me. Well, that's good. You're probably tired of looking at me. But at least you heard my discussion. Okay, so now let me hold it. My antenna's getting in the way here. Hold it in front and kind of scan over. Ah, there it is. My antenna. Stop. Okay, there we go. And so there it is. And in fact, I see how blurry they are. They're really close together. But you see how far I had to scan? Because there wasn't anything right in this area. There wasn't any of the blues. And so here's the original light. And so remember that d sine theta. And my angle has to be bigger, so I have to come over really far to get to the longer wavelengths. And so the blue would have been right about there, but there isn't any. But now there's some yellow and some oranges and some reds, and then kind of all blue blurred together. All right, well, now I guess I will say, let's call it quits. I will zoom out and say, let's call it a 15-minute break. Let's come back after this, and we will then do some example calculations. Although we've done a few, so maybe we'll just do like 4 or something like that. All right, we'll see you in 15. All right, hey, welcome back. Our break is over, and I've erased the board and even put some new ink in my marker here. And let's go ahead and do some example problems. And so again, I'll just try to keep it on this one little board here. Hopefully it won't be too complicated. But I wrote down 4 examples, including, as I was saying right before the break, I probably should show you for ones that have a higher atomic number than just the the hydrogen that I was showing you. All right, so let me turn on the screen here. Oops. I guess I forgot to warm it up here. All right, so give that a sec to warm up, but I went ahead and I said, let's try number 7 as our first one. And I will also say that number 7 is, interesting. Is it warming up? Okay, good. So number 7 is really one I already did. So I won't do the whole thing, but I'll just kind of remind you and lay it out again here. It says, calculate, by calculating the wavelength, show that the first line of the Lyman series is in the ultraviolet. Okay, so if you remember, the Lyman series was the one that I said if I did an energy diagram, and we're looking at hydrogen, and n equals 1, and so the energy level here at n equal to 2, and get a little closer together, n equal to 3, and n equal 4, and so forth and so on. But the ones that terminate or stop in n equal to 1 is the Lyman series. So the first one would be from a 2 to a 1. And then the other ones would be even higher energy and therefore shorter wavelength. And so, as I was saying, and even showed you mathematically before the break, is that if the 2 to 1 is such a high energy that it's in the ultraviolet, the other ones are even just more so. And so none of these are going to be visible. And that's what this question is saying. So let me just remind you that the change in energy of the atom would be the final energy of the atom minus the initial. And that the energy of the photon is negative of the change of energy of the atom. So in other words, where does the photon get its energy? It gets it from the atom. So if the atom loses energy, so we want that to be negative so it can go to the photon. They're equal and opposite. I say that because your author will often write then that the energy of the photon is, and he takes the negative of this, and he says it's initial minus final. And as I was saying, and just thought I would repeat here in this problem, students they look at that and they go, well, that's not right. Isn't it supposed to be final minus initial, not initial minus final? And we'll say, well, yeah, it's final minus initial for the energy change of the atom, because this is the energy of the atom. And so it's the opposite of that. So initial minus final for what goes to the photon. Okay, so the photon, we said, has an energy of hc over lambda. And the energy for hydrogen is negative 13.6 electron volts over n, and then this would be initial squared. And then so minus a negative 13.6 electron volts over the final squared. So it depends how you write it. I know that before the break then, I put the two negatives together and put it over to here, 13.6. And it's kind of nice to write it this way, because it does kind of look like final minus initial this way. However, what's confusing then is it doesn't have the negative for the energy. And so where did that go? So it's final minus initial, but it's the opposite of that, which is why it's the photon. And so this 1240 electron volts nanometers over the wavelength. And so go ahead and put in your final as a 1 and your initial as 2 for the first one in the Lyman series, and do that calculation. And we did it before the break, and I think we got like 122 or 121, something like that. And so that was the wavelength for the longest wavelength, or the lowest energy, and all the other ones would even be shorter wavelengths. So I'll pause on doing all those calculations and say, all right, that's a good review, if you will. Let's try number 11. So that's the second one here, kind of in this area on the Bohr atom and calculating energies and wavelength. And it says, if a hydrogen atom has its electron in the fourth state, how much energy in electron volts is needed to ionize it? Now that's kind of the other direction. Instead of the electron tumbling down, if you will, and the atom losing energy, and of course giving it to a photon, now we're saying, what would it take to give, and how much energy would it take to give to that atom to energize it? And it doesn't say where that energy has to come from, but of course one option would be to hit it with a photon. And so to shine a laser or even a light, and if the light had multiple colors, the one of the right wavelength and the right energy would make it transition. So for this one, I'll just put here number 11, but I'm going to use the same energy diagram because we're still talking about hydrogen atom here. And I'm going to say, okay, so remember this is a negative 13.6 electron volts here. And this would be the 13.6 divided by 4, which I know we did earlier, but I don't remember what it was. Oh yeah, 3.4. So this would be negative 3.4 electron volts. We even did the n equal to 3. The one we didn't do is the one I need to do for this problem is what happens if n equals 4. So I'll do both, 13.6 divided by 9. And this was a negative 1.51 electron volts. But the one I really want is the 13.6 divided by 4 squared, which is 16. And so that would be negative 0.85 electron volts. Okay, so what they're saying here is the electron, and maybe I'll draw a different color to kind of indicate, is right here. Now, this is not a drawing or a diagram of physical space. That's not physically where it is, but it's got that much energy, which, of course, it means if you left it alone, it would transition from a 4, and who knows, it might go 4 to 3, it might go 4 to 2, it might go 4 to 1. If it did go 4 to 3, then once it's in 3, it might go 3 to 2, or it might go 3 to 1. And if it went 3 to 2, then it could go from 2 to 1. And so, what is that, 6 different combinations? 1, 2, 3, 4, 5, 6. Yeah, so there's 6 different photons that could be given off. Now, not by one single atom, okay? And so the most that could ever be given off by this one atom would be 3 photons, where it went 4 to 3, 3 to 2, 2 to 1. Any other transition, like all the way from 4 to 1, would only give it 1 photon, but it would have all of its energy. But my point is, as we saw before the break here, as I, put gas of hydrogen in here and pump electricity to get him to that excited state. This is the neon again. That's where we left off. But you would then see some of the atoms giving off energy as 4 to 1, but some of them would go 4 to 2, and some of them would go 4 to 3, and some of them that went to the 3 would now go 3 to 2, and once they got to the 2, they'd go 2 to 1, or the ones that went 4 to 2 would then go 2 to 1. And so of all those 6 combinations, they would all happen, and of course then you would have 6 different colors, and that's only if you're an energy level 4. You can imagine 5, 6. So there's a lot here, and that's what I'm saying here is there would be a unique set of patterns. And of course, that's why we're talking about, again, before the break, that this would be a way to identify, like helium, on the sun, even though if you never really found it on the Earth. Just by looking at this unique set of patterns and realizing we've never seen any of that pattern here on Earth. So there must be another atom, another type. And since it's in the sun, let's call it helium. Kind of makes sense. But this one is asking the other direction. So this one is saying, how much energy would you have to give it to get it free, to ionize it? And what that is saying is give it enough energy to get to 0. And so obviously, it is just 0.85 electron volts. It has a negative 0.85. How much do you have to get it to get to 0? You're in the hole 0.85. You've got to give it a plus 0.85 to get it out of there. And so I would say the energy to take to energize it is 0.85. And in terms of chemistry and stuff, that's a small number. So this electron is already gained a lot of energy. It's not completely energized, but remember, completely energizing the electron for hydrogen would take 13.6, and we already gave it a lot. We're just shy of that by 0.85. So just 12 and something is what was already given. And this would then just take a little bump from another atom, and it would be ionized. This one's ready to be ionized. It is so darn close. It would be hard to keep it from not ionizing. Although I got to admit, it would be hard to keep it from not tumbling back down and giving off the photons, because that's what it's going to want to prefer to do on its own. All right, so that would be number 11. Let's jump to number 28 here. So 28 is kind of down this road that I wanted to do and say, okay, excuse me, what would happen if, excuse me, we had a higher atomic number here. And so this one again, especially for you guys in the life science and, you know, making these x-rays, or at least using these x-rays with your analyzing your life science here. It says the maximum characteristic x-ray photon energy comes from the capturing of a free electron into the K-shell. Now again, that's some old technology, but for x-ray technology it still seems to be used a lot. So remember, K-shell is n equal 1. K-shell is the first orbital. So it goes K, L, M, N, 1, 2, 3, 4. Okay. And so they're telling us something very important here. They're telling us that a free electron then gets captured into the K-shell valence. What is the photon energy in keVs, kiloelectron volts? And for any of you who've worked on these x-ray machines, I know when my son broke his arm, and more than once, and more than one son, I always like to kind of go into the little room with the x-ray technician and watch the dials and say, okay, hey, what are you setting those at? And, you know, and they have this choice of how many keVs are they going to apply, and how much energy are these, and then for how long. And so there's an art in taking a good x-ray, depending on something thick like a body cavity or something thin like a hand, and, you know, what energy level and how long. And that's one of the things that is taught to the x-ray technicians. And so, and the combination, you know, is also important, the product of the two, because that's the total energy exposing the patient to. And so all these things you learn in an x-ray technician kind of course and discussion. But I noticed all those dials are set, and I've worked with some students who are in our x-ray technician course, and so they always talk about things in keV. So it doesn't surprise me that we're looking at photon energy and high energy. These are x-rays. These are not 1 or 2 or 3 EVs like we did for our optical region. These are thousands of keVs. So that's why, or thousands of EVs, that's why we call it keVs. And it says go ahead and treat this free electron as having no initial kinetic energy. Okay. Somewhere in here, I think I overlooked tungsten, because that's important. What is the photon energy in keVs for tungsten? And so what we're going to do, like you saw me do examples in the last chapter, the electron gun, is you're going to take a metal wire and pass electricity through it and boil off electrons. Then have a metal plate that you charge up to a voltage in keVs, and you shoot it through, and then you hit a target like tungsten. And when it hits that electron gets captured, or it knocks them off and that electron gets recaptured. And in the process of getting recaptured, it gives off a photon. So we're talking about the same kind of process that I've been doing for the hydrogen atom, but now we're just going to do it with tungsten. Okay, so let me move that out of the way. And of course, completely change my energy diagram, because this is the energy diagram for Z equal to 1. This is the energy diagram for hydrogen. And in general, then, the energy equation and the diagram would look like this. Energy equals negative, and there's that Z squared we were talking about, times 13.6 electron volts over N squared. All right, and so I need to apply this to tungsten. Now also I want to be a little careful here. If I were to draw tungsten, and so maybe I'll put the nucleus here, and kind of look over on the periodic table, or maybe for you guys I should come back over here and say, okay, let's look at the periodic table. I won't pull down the screen here, but tungsten is right here, number 74. And so it's important to know that there are 74 protons in here. Okay? Well, let me turn that off now that I have the number. And so Z equals, well, not quite 74. Remember I said during the break that I should really do an example like this, because it's really kind of the effective charge that the electron sees. Here's what they mean by that. So imagine there are 74 protons in here, and you've got this free electron floating around out here. Now it's floating around out here because in the lower shell, the K shell, before you got the tungsten excited, and so I'm just kind of looking over on the periodic table, and yeah, maybe I should put it back up here. But you'll see how many shells are here, and tungsten, where to go right here, is at the level 6. And so this would be the first shell, the second, the third, the fourth, the fifth, and then the sixth is only partially filled. And I won't bother to try to draw all the electrons in there, but the first 5 shells are completely filled. In fact, let me just come across here my periodic table. 5 is 54. So 2 on the first row, and then 8 more in the second one, and that's what we started at the beginning of our lecture. So 10 of them would fill up the first 2 shells, which you might call this the K shell and the L shell. Okay, then the next shell, the M, or the third level, I guess we could look across. It looks like it has 8 more. So that's not a real hard one. However, here's where the periodic table gets a little messy, because it's down here. These are actually in the third shell, but they're higher energies, and so lower in the periodic table than the 4. So actually 2 electrons would go into the fourth first, then we would get another 10 in a d orbital here. And it's hard to draw it on here, and I probably should stop, because at this point, without getting into the shape in 3 dimensions, you're going to wonder, well, where are you going to put these other 10? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And it just looks silly, and it's kind of wasting your time here, and so I'll turn that off. I just want you to realize that there's a lot of electrons here, but when they say that it's going to be X-rays from the K shell, from a free electron, they're talking about an energy transition that is a free electron down to the K level. Now, there is something here that we didn't get a chance to talk about. It's called the Pauli exclusion principle. Once an electron gets in a certain spot, it's kind of like seats in an auditorium. Once somebody sits in the auditorium, it's full. You can't put a second person there. And so the way I've drawn it, it's all full. But what would really happen in the real world is your tungsten, so if this is a tungsten atom, you would have your electron gun shoot the electron and hit the tungsten. And what it would do is that electron that comes in hits, and if it were to hit one in the K shell, this one, it would knock it out to here. And that's actually perfect for what we want in generating X-rays, because what we now have is an electron way outside of the atom. It's been ionized. And the one that's missing, the open seat, is way up here up front. All the other seats are full. And so the only thing this electron can do is to go into this position. It can't go into the second orbital, the L or the M or the N or the O or the P. It can't do those. Those are all full. Well, out here they're not full, so it could do something like that. But for these other ones, they're all full, and it would want to go all the way to the K shell. So it does that, and because of that, it goes all the way into the lowest orbital. It changes its energy significantly. All right, so to solve this problem, I will say that the energy of the photon is then equal to negative of the change of energy of the atom. Now remember, the atom is final minus initial, so negative of that would be the initial energy minus the final. And the equation I'm going to use for the atom is going to be this with a z squared. It's going to be the energy of the tungsten. So when I talk about the initial energy, it's saying it is free. It has been all the way kicked free with very little kinetic energy. That's what we've been talking about. That would be zero energy. Or maybe put it another way, it's been kicked up to such a high orbital, this number here, n, is like 1,000,000 or 1,000,000,000 or 1,000,000,000,000 or infinite. And when you have a big number and you square it, this is essentially zero energy. And so the initial energy is zero. And again, I'll say it sounds weird, but to say that the initial energy is zero, again, sounds weird, but that's a lot of energy. So this electron that is completely unbounded, it is free from the atom, has a lot of energy. It has zero. Because now it's going to tumble in and have a big negative value. So there's going to be a big change and release a lot of energy and release a very energetic photon. It can't tumble down level to level and spread that energy over many photons like we were talking about for the hydrogen atom, where it didn't have all the other pieces full. These are all full. There's no place for the electron to go but right here. So with that in mind, what is the final energy? And let me use this equation. So it would be minus a negative, and then I have this z squared. And this is the part that I really wanted you to see and was talking about for the break, because I'm going to put 73 here, not 74. You might say, well, doesn't this have 74 protons? And I'll say, well, yeah, it does, but it's being shielded by this one other one that's in the k orbital. So its net effect is 73. When this one comes all the way in, these guys don't shield it anymore. Remember how we did our electric field back at the beginning of this semester? And we said if you're in a spherical shell and you get inside, they balance each other around the shell. And so even though I have another 73 electrons on the outside, those don't count. But it's the one on the inside that is not shielding. And so that was our spherical shells and our shielding. So even though all those other electrons, like I said, they're not shielding anything, when you get in here, this one would view it as if there's 73. Not 74, because this one would be kind of on the inside and helping it shield. Now, probably not perfect, so it's probably better to have something like 73.2 or 73.3. And so if you really wanted to go and make a measurement, you could find out the equivalent charge. But that's what we should call it, is the equivalent or the effective charge that the electron sees. And so I'm going to guess that it sees probably about a 73. And I would say that that one inside probably doesn't shield it perfectly. So I would think from an experimental value, it might come out to be like 73.2, the equivalent of 73.2 or 73.3, or maybe even 73.5, but definitely not 74 and definitely not 73. But probably better on this to guess 73 than to 74. And that's how your author suggests we solve this. So I'm going to put a 73. So it's 73, and I just wanted to emphasize why I'm putting a 73 and not a 74. That's why I wanted to do that. Now the rest of it's pretty easy, because then this is the 13.6 electron volts, and of course this is the final position of it. And since they said K, oh, be careful, did they say K? Yeah. What is the maximum characteristic X-ray photon coming from the capturing of a free electron into the K shell valency? What is this energy in keV for tungsten, assuming that the free electron had no initial kinetic energy? Okay, so there it is. The two negatives make a positive. Let me grab my calculator here and take the 73 and then square it, and then the 13.6, and then divide by 1. And that is 72,000. Roughly 500 electron volts, so I'll just change it to 72.5 keVs. And so that's going to be our characteristic X-rays. That's going to be what you call the most X-rays that are there in the machine. There are other ones. Like I said, this is kind of a little bit of a random process. Some of the electrons would actually, fall here. Some of them would just move around and bounce around, and we're back to last chapter where we did our free body diagram. And so you would probably see a spectrum that would look like this. There's our free body diagram, plus this characteristic X-ray. And so that would stand out with a huge intensity. And so you would have a black body radiation background and then a big spike of a massive amount of X-rays at that particular quantum value. And that's what you really want. The other ones just we have to live with because we're just statistically bouncing things around. All right, well, let's try one more and call it quits. The next one is kind of along that same line, and so let's try number 29 here. And 29 says, what are the appropriate energies for the K alpha and the K beta X-rays for copper? And so I thought this would be a good one again because it has a Z in it, but it also now we're looking at copper instead of tungsten. So we're shooting our electrons into a copper target and we're going to make X-rays based upon that. But they also have a neat little description. They call this the K alpha and the K beta. And so this will give me a chance to kind of talk about a little bit more about complicated atoms here and some of the terminology that you medical people use. And so these X-rays are again generated with some kind of element, in this case copper, that has a high Z number, so that the energies are high, because you wouldn't get these kind of energies for the simple case of hydrogen, or even the ones I showed you, which had, helium was my biggest one at Z equal to 10. I don't think anything's going to be in the X-rays for those. UV, yes, but X-rays, no. So I got to get to a little higher ones, and copper's a good place, and copper has a lot of other nice properties, but again, tungsten's the better one. It's got all the best properties here. All right, so number 29 then, and I'll just put this on the board again. Energy equals negative, and there it is, Z squared. 13.6 electron volts divided by N squared. So that's the energies that the electrons have at this higher energy state. And they use this phrase, the energies of a K alpha and a K beta X-rays. And here's what they mean by that. If I do it in an energy diagram, as we said, N equal to 1 is the lowest. And that's the K value. So what they're saying here by saying K alpha or K beta, they're saying the electron tumbles down and it finishes at the K level. And that's the one that's going to give us the most energy. It's the one that's all the way in, real tight. And so if I try to draw copper here, copper is going to have 29 protons. And copper, 1, 2, 3, 4, is in the fourth shell. 1, 2, 3, 4. And if you will, I'll switch back so you can see a periodic table. But here's copper, right here, 29. And you can see it's the fourth level down in the periodic table. So that's why I drew it like this, 29 protons, 4 shells. But remember, the inner shell is the K one. So it's going to finish here. So I will put one electron that remains there and maybe an open spot. So we got to get rid of that one. Remember I said electrons are like theater seating where you can't put one there if there's somebody already there. And so we got to get it out of there. And that's normally how we do this. This is why we would put a target made out of copper and we would shoot electrons at it at a high rate. It would hit it. And the electron that came in that hit it, that's not going to really count for much. But the idea is you'll hit one at the K shell. You'll probably hit a bunch of other stuff too, and that's why you get that whole black body radiation stuff I was talking at the end of the other one. But the magical one was this one right here, and you would kick it out. Now the problem we did before, we kicked the electron all the way out, and we probably would do that again. But the problem we did was to say, let's let this electron jump back all the way in. But another thing that can happen, and so let me just go to the second level, so the L shell. is that instead of this free one coming all the way back here, somebody else in the auditorium says, hey, let me go there. And so once this seat opens up, someone says, I really want that seat. And so they move forward. Of course, that opens this one up, and so maybe some other ones would move in. And so there's, again, all kinds of X-rays that would be generated in this process. But what's called the K alpha, and alpha being the first letter of the Greek alphabet, is the one that would then come from the next level up, the L, and go into that open K seat. So we use the K because that's the place where it's going to terminate at. But we use the alpha to saying this is the first one in the series, like the Lyman series we were talking about. This is the lowest one. And then there would be a K beta. And so the beta one would be one of these electrons coming from the M shell and going into the K. And so maybe I'll label this as n equal 1, n equal 2, and n equal 3. In my energy diagram, I guess it would look like this. So at n equal 2, this transition right here would be the K alpha. It would be terminating at n equal to 1, starting at the next level up. And level 3 would then be K beta, where again, you're ending up at the K shell, and you're coming from the next one up, the level 3. And there would be a K alpha, beta, gamma, delta, epsilon, eta, zeta, theta, you know, the whole list. And they would all be coming from higher energies up. And again, the most extreme one was the problem we did last time, where it came all the way from a free electron. So this isn't going to be nearly as energetic as the last one for two reasons. The first one is we're not going all the way from a free state into the K level. We're going from L to K. But the other one also is we don't have nearly as much charge as the tungsten. So these are going to make soft X-rays. These are going to be low energy X-rays. And so that's probably the reason we put a copper target, is so that we can make X-rays, but not nearly as energetic as the ones we want. Okay, so if that made sense to you, let me leave this energy diagram here and kind of erase this picture and say, all right, let's give this some effort. And so, like we have done with the other problems, I'm going to say the energy of the photon is equal to negative the energy of the atom. And of course, for the atom, we would go final minus initial. But with that extra negative in there, it becomes initial minus final. And so there is the energy of the photon. And of course, if we wanted to know the wavelength, and we don't, so I won't go that far, we would do hc over lambda. So let's look at the energies of these X-rays. And again, starting with the initial and then using this equation. So the initial energy would be negative, and then let's have that same discussion. I'm going to do a z squared. And I guess I erased my picture. But again, this is the effectiveness of it. There's actually, as we said, 29, let me double check, yeah, 29 electrons. But if the one electron comes in all the way to the inner orbit, the K orbit, it's actually protected by 1. So instead of being 29, I should probably put a 28. And since it goes inside, the other ones don't protect it. Okay, that's our shielding effect. That again, we talked about at the beginning of the semester, a spherical charge, it gets protected on the inside, or there's no electric field on the inside, it's only on the outside of the sphere. So there's the 28 and then the squared. Let's see, 13.6 electron volts, okay. And initially then it is at state number 2. Again, this is why we call it the K alpha, because it goes from 2 to a 1. So it starts at number 2. So then minus a negative 28 squared, 13.6 electron volts over 1 squared. And so grabbing my calculator and noticing that 2 negatives make a positive, I'll enter this one into my calculator first. So right here, I'm going to go 28 and square it and multiply it by 13.6, divide by 1, that's that term. Then I'm going to subtract, and it looks like I've got a 28 squared and a 13.6 and divide by a 4. And so this is 7,996.8 electron volts. Maybe to 3 significant figures, it would be 8,000, and so I will write it as 8 keV. And if I remember right, the last problem was 72. So as I said, this should be a lot less than the last one. Now, the other half of this is this K beta, which is going from number 3. And so we would have that one. And so let me look at the energy of this photon. I'll call it the K beta. And let me save a little time by not writing it all out, but it would look something like this. I shouldn't have hit cleared. I could have just edited it. Oh, but 28 squared times 13.6. And then that minus 28 squared times 13.6 divided by, and so this would be starting at number 3. And 3 squared is a 9. So I'll put a 9 and hit enter. And so this should be more energy, and it is. It looks like it is 9.48 keVs. And so a little bit more, but still way less than the last problem where we had tungsten and we had a free electron all the way to the inner K shell. All right, so I hope that helps with it. I guess I will call it quits and let you start working on the homework and ask any questions that you might have. Let me circle around here and shut off the camera, and I will then see you for tomorrow's lecture. All right, take care, everyone.